Assalamualaikum and greetings everyone. Today's topic is on conservative vector field, which is the third section of this chapter. A vector field F is said to be a conservative field if and only if, so here we have 1, 2, 3, 4 bullets. Those are properties of a conservative field. Now let's look at the first property. A vector field F is said to be conservative if the vector field does not circulate. So if the vector field does not circulate, then it is a conservative field. And to tell whether there is circulation or not in the vector field is to check for the curl of F. So del cross F is curl of F. So if del cross F gives you a zero vector, then there is no circulation in the vector field. Hence, F is a conservative field. Okay, now the second property for conservative field is the line integral F dot dr does not depend on its path. Okay, so this is different from the regular vector field F, because the first property for line integral is it is dependent on its path. But if F is conservative, then it does not depend on its path, meaning that it doesn't matter what path it takes, the value of F dot dr starting from point A to point B will be the same. Okay, so that is the second property. F dot dr does not depend on its path. Okay, and the third property is the value of any line integral of closed curve is 0. Okay, so this is also different from the regular vector field, because here in the property number 3, line integral around a closed curve, what you need to do is you need to evaluate on each curve and then add them together. But if F is a conservative vector field, straight away you can tell that the value of line integral of a closed curve is 0. Okay. Now the last property is quite important, this one. There exists a potential scalar function phi such that F is equal to the gradient of phi. Okay, so if you have the scalar function is called potential function. Let's say it's phi, and it can be in terms of x, y, and z. So the gradient of phi, as you recall from the previous chapter, is partial phi partial xi plus partial phi partial yj plus partial phi partial zk. And this is equal to the conservative field F. Okay, so if F is a conservative field, then there exists a potential scalar function phi such that F is equal to the gradient of phi. Okay, so to determine if a vector field F is conservative or not, it is enough to show at least one of the properties above. So usually we show that del cross F is a zero vector, and that is enough to show that F does not circulate, hence it is a conservative field. Alright, now there's a theorem, a very important theorem. It's called fundamental theorem for line integral. Okay, if F is a conservative field and the potential function is phi, then okay, here the notation is not quite right because everything is bold. Here's the correct one. So we have a vector field F dot with dr. Okay, so dr is a vector, and from point A to point B. So instead of evaluating the line integral F dot dr, if F is conservative, then you can use this fundamental theorem for line integral, where this is equal to the potential function at point B minus the potential function at point A. So this is called the fundamental theorem for line integral. So instead of evaluating line integral, we use the potential function to find the work. Well, you know, F dot dr is equal to work done. So potential function at the destination point minus the potential function at the initial point. So that is fundamental theorem for line integral, and these are the properties for conservative field. It is enough to show that del cross F is a zero vector to show that F is conservative. And the fourth property is important. There exists a potential scalar function phi such that the gradient of phi is equal to F. Okay. For example, I'm gonna save that in our next video. Thank you.